Thank you. Good morning. I am actually Andrew Gelderloos. That's all right. Usually people mispronounce the last name, not the first name, but good. You got the last name right. I'm a master's student at the University of Utah, and this morning I'm really excited to present my research showing how landscape adds predictability to water resources. So water resources are really important, but they're facing some big challenges. Temperature is Temperature is increasing and climates are changing. This is making the supply of water more and more uncertain. At the same time, the population, especially in the West, is growing, and so the demand for water is also increasing. So in Utah, these pressures challenge the future stability of water resources. But Utah has identified these threats and acknowledged that we need to be working towards solutions. One good example of this is the recent draft state water strategy that was just released from the governor's office. And this covers many issues, some of which can be summarized by two questions. How will climate affect water supply? And how will our water supply satisfy demand? And these are some pretty big questions, and it's going to take a lot of people working in a lot of different areas to come up with solutions. Kind of like all the people we have here at the Watershed Symposium and all the different topics that we're going to hear about today and tomorrow. And I believe that to solve these two problems, these two questions, there are three main categories of work that we're doing that must tie together. First, we have people working on the climate inputs to our watersheds. Temperature, precipitation, and other climate. It's important to know what the climate of our watersheds will look like in the coming years. And the second group is really focusing on how that precipitation is partitioned or routed through the watershed. And so they're asking the question, how will these climate inputs be translated into water resources? Because we know that the precipitation that comes in is going to eventually come out as streamflow maybe, or evapotranspiration, and it's going to take a lot of different routes to get to that endpoint, and that all is going to affect how much water is available. Which leads to the last group, which are the policy makers working on how we best manage our water resources. And they need to know how much water will be available, which is a combination of both the climate inputs and that understanding of how the water moves through the system to become available to us. My research in particular is focused on this second part. How is the precipitation partitioned or routed through a watershed? But in order to keep it more broad, I know I need to link to these other two categories, and so my research is also identifying the climate factors that are influential in the routing of precipitation, and my work also shows how we can better predict water supplies so that policy managers can better manage water supplies. So my question is simple and straightforward. Where does the precipitation go? More specifically, I'm asking, are all watersheds created equal? So will the routing of precipitation through different watersheds result in similar output? And if not, what are the important processes that are controlling that movement of water through the different watershed systems? And so to test if the routing of precipitation is dependent on different landscapes, I need to find watersheds that have similar climate patterns but different landscape characteristics, which conveniently leads me right here to the 7 Wasatch watersheds, and you know them. You're probably from this area: City Creek, Red Butte, Emigration, Parleys, Mill Creek, and the Cottonwood Canyons. You can probably picture some of these in your head, and you realize they don't all look the same. You know, you can go to one and you're not going to see the exact same thing as the other. So they have different landscapes, but they're also located pretty close to each other, so we can assume that they're probably going to have similar climate patterns. Additionally, what's great is that each of these watersheds has about 100 years worth of climate and stream flow data available. for a total of 711 years of data between all of them. Now, to work with this data, I had to take the data and normalize it by the area of the watershed so that I could compare the different amounts between watersheds. So I took the precipitation volume and weighted it by the area of each watershed in order to come up with a depth. And I did the same with Streamflow so that they're all comparable. And so let's take a look at this data simply graphed over time to see what it looks like. First, we have precipitation. And we see that precipitation varies in the different watersheds. So we have different amounts in different watersheds based mostly off of elevation differences. And at the same time, we have similar temporal variability. So these lines mirror each other. The line for Little Cottonwood mirrors, the other ones, just at a different magnitude. And we also notice that there is no trend over the past 100 years in precipitation. We're not increasing the amount of precipitation or decreasing over time. Next, we can look at temperature, and again, we realize that the watersheds have different temperature, mean temperature values every year, and they also follow similar temporal variability patterns. But what we notice that's different is that in the past 50 years, the temperature has started to increase by about 0.4 degrees Celsius per decade. When we look at streamflow, we see, again, big differences between the watersheds in terms of the amount of streamflow. But what's different from the climate that we saw is that there's higher spatial variability. So these lines aren't necessarily mirroring each other as well as they did for the climate. At the same time, thinking back to the trend we saw in temperature, we don't see that at all here in streamflow. There's no trend over time. So right away, we have two takeaways just by looking at the time series of our precipitation temperature and streamflow data. We see that there is, the streamflow shows evidence of differential influence of landscapes between the watersheds, since it's more variable than the climate. And we also see that there may not be a huge impact on temperature on streamflow. So we'll think about that as we keep going here. So I want to look at what controls streamflow. And I looked at all the different climate factors, and not surprisingly, the one that came out as the best predictor of streamflow is precipitation, which should make intuitive sense. When we have less precipitation, we get less streamflow. When we have more precipitation, we get more streamflow. And we see that that relationship can be modeled by these lines, these best fit lines that I have on there. And if you remember that first takeaway point that I said, that the landscapes are differentially filtering the climate, we can see that here because we see that the relationship between precipitation and streamflow is not the same for each watershed. We have different slopes to these lines, and we have different best fit lines. At the same time, while we can predict streamflow, we're not predicting it with 100% accuracy. So we see that there's some variability around these lines in that the points don't all match entirely 100%. So we can quantify that variability right here using the R-squared, a measure of the goodness of fit of each of these predictions. And what we see is that we're predicting streamflow using precipitation with about 40 to 60% accuracy. And it's not the same, we don't have the same accuracy in all of the watersheds. For example, Emigration, the R-squared is about 0.46, whereas in Little Cottonwood, it's about 0.74. So there is a range of variability there. So what is controlling this remaining streamflow variability? That's the logical next question to ask. And again, you can think of all these different climate influences that could control the remaining variability. And when we think about streamflow and we think about what is affecting it, a lot of times we jump straight, after precipitation, we jump straight to temperature. And we think temperature is going to increase in the future probably, and so we're probably going to see something of that in the Streamflow. So I wanted to look and see if we do see that. And so how do I do that? Well, we have our precipitation and Streamflow data, and we have a best fit line, but our data does not all fit or fall on that line. It is some distance away usually. And so we can quantify how variable the data is and how far away it is from that line using the residual. And the residual can either be positive if precipitation underpredicts streamflow, or it can be negative if precipitation overpredicts streamflow. And so if temperature is influencing this residual value, then we would expect that the warmer temperatures would all have negative residuals and the cooler temperatures would have positive residuals. And so, of course, I graphed that up for you to see here, the residuals versus the mean temperature. And there is no relationship, which is probably pretty surprising to you if you think temperature is going to affect streamflow. This shows that after precipitation, temperature doesn't account for any of the variability. And so maybe you're not totally sold because maybe you think that our water resources are affected more in the winter than in the summer when we have our snowpack sitting up in the mountains. And so I looked at the winter temperature, not just the annual temperature, and again, there is no relationship. But then half of you are probably thinking, why is he doing winter temperature? He should have been doing summer temperature, because that's when we have vegetation growing. And so I looked at that, and again, there is no trend there for any of the watersheds or for all of them overall. And so maybe temperature is just thinking too much into it. Maybe it's just the seasonality of the precipitation. And when we have more snow, maybe we'll get more streamflow. And so maybe it's that winter precipitation. And again, the winter precipitation also does not have any effect on those residual values. And so now I'm sure some of you are probably thinking he's going to summer precipitation next. And yes, because, well, summer precipitation, maybe we have, you know, all that rain coming down in the summer and it's just going to go straight to the plants and not end up as streamflow. So is there a relationship there between summer precip and residuals? And again, no, there is no trend. And so you haven't seen any trends yet. Maybe you've picked up the only trend here is that no simple climate variables are predicting that, that residual value. And I could show you some more graphs that also don't have any relationship between climate factors and residuals, but just know that I looked at all these things and none of them added predictability, except for two factors here, the annual base flow and the snowmelt rate. So I'm going to talk about those some more. First, the base flow. So this is a characteristic hydrograph that we see out here in snowmelt dominated systems where we have a peak here in the spring from snowmelt, and then after that peak we see that the streamflow goes back down to what's called a base flow. And if we look more closely at that base flow, we see that the base flow is variable between years, and that variability is due to antecedent storage conditions. And so is this antecedent storage helping us to predict streamflow? And so I looked, and yes, when we have lower base flow, the precipitation overpredicts here. When we have lower base flow, the precipitation overpredicts the amount of streamflow. And when we have higher base flow, the precipitation underpredicts the amount of streamflow. And this is just an example from City Creek, but this is true across all the different watersheds. And we can see that the base flow adds some more predictability by increasing our R-squared, our goodness of fit, in all of the watersheds across the board. But we see that it doesn't increase it by the same amount. The base flow has a different effect in different watersheds, suggesting that something about the subsurface characteristics, maybe like in Little Cottonwood, you think of all the granite and the igneous rock that's there. whereas in emigration, we have a much more sedimentary system. And so some of those landscape differences are influencing the amount of predictability that this antecedent storage adds to our streamflow prediction. So now we're predicting streamflow with 60 to 80% accuracy, but can we do better? I think we can. So we're going to move on to the snowmelt rate here. And what we see in these graphs is snow accumulating and then melting. And the same over here, accumulating and melting. And we see that the snowmelt rate here is different in different years. It's different in different years and in different watersheds based on the topography of the slopes. Since snowmelt rate is controlled mostly by solar radiation, we'd expect that if the slope aspect of the watersheds is different, we might get a different snowmelt rate. And also by humidity, we might expect different values for different years, which we do see different snowmelt rate values in different years. And so does that variability add predictability? And we see that yes, when the snowmelt rate is slower here, again, the precipitation is over predicting streamflow. And over here, we see the opposite. And this is again City Creek, but it's true across all the watersheds. And we see that it adds more predictability. The snowmelt rate further improves the predictability in all of the watersheds. Again, not to the same extent in each watershed, but it is still adding predictability. And now we are predicting the streamflow values with an accuracy of over 85%. So we've gone from 40 to 70% to 85%. So let's kind of see how far we've come here. We took 711 years of variable climate data with precipitation ranging from 400 to 2,000 millimeters. So that's a big range. And temperature ranging from 1 to 10 degrees Celsius. Also a huge range, larger than any of the wildest climate change projections. So we have a range here that's very large. And that climate variability is dispersed over 7 unique watersheds with different elevation, different geology, vegetation, and soil types. Yes, this is the 7 watersheds from City Creek down to Little Cottonwood. And we have the streamflow data, and we want to predict that streamflow data. But using precipitation, we can only predict it so well. But adding 2 more simple variables, we can reduce that uncertainty in our prediction to about 10%, less than 15%. And so what we found is that landscape does influence water resources. We can't just assume that climate variability is going to be filtered the same in different watersheds. And this landscape, the landscape that influences this water resources is elevation, which influences how much precipitation falls in the watershed, which isn't too surprising. And also the subsurface characteristics, how much water can be stored within a watershed. And also the topography, which is affecting the snowmelt rate. And so if we want to go to another watershed where we don't have 100 years of historical climate and streamflow data, we need to take into account the elevation, the subsurface characteristics, and the topography in order to make better and more accurate predictions of our water resources in those watersheds. Thank you. Any questions? Yeah. Mm-hmm. So the takeaway is that this base flow has fact this base flow variable has added predictability, but we need to understand what that base flow is, why that base flow is adding predictability. And it's adding predictability because we have uh, different geology in our watersheds. And so what we need to do if we want to better predict water resources, we need to characterize that subsurface, uh, those subsurface characteristics, and we can use that to determine whether or not base flow is going to add more predictability to our stream flow. Like in Little Cottonwood, we saw that it didn't add too much predictability. Precipitation really explained a lot of the variability. And so we can use this to determine which different landscapes are going to have, in which landscapes base flow is going to have more, or the storage is going to have more of an impact. Does that answer your question? Yeah. Mhm. The snowmelt rate is I I haven't seen that there are trends in snowmelt. I could be in the snowmelt rate. I could be wrong because the snowmelt rate isn't necessarily dependent on temperature. It's yeah, it's dependent on the soil radiation. Mhm. Yeah, yeah. So some of my future research uh, is to look at what exactly is it about these landscapes that are really influencing the snowmelt rate and the subsurface storage to because those seem to be the really important things in water resources. So, yeah, yeah, that's the data that I have that shows there's no trend. Yeah, maybe um, I've this is data over the water year, so from October to September. Yeah, and um, so maybe we can talk afterwards. The temperature data is Prism modeled data. So so what the Prism does is it uses all the watersheds in or all the weather stations in the area, and it interpolates values across all the watersheds. So using that, I was able to get complete coverage of all the watersheds. So it's a modeled climate uh, data, but it's accepted and used in many different areas. So yeah, so the model data is it does in their uh, algorithm try and take into account where those uh, weather stations are located, and it also takes into account the elevation, the slopes, and aspect, the different things like that, to try and interpolate across landscapes that are variable, like the watersheds that we have here. By the way, if you do have more questions, I do have a poster over there in the poster session, which I believe is at 2 p.m. So if you have more questions then or anything specific, come see me at 2 p.m.
All right. Well, let's wish him a round of applause.